So good morning students. Today we are going to solve a numerical problem on the slider crank mechanism, and let me tell you the problem first. So please note down the problem. So in a slider crank mechanism, the crank is 480 millimeter long. The connecting rod is 1.6 millimeter long. .6 meter long, the connecting rod, and the crank is rotating in anti-clockwise direction with angular velocity of 20 radian per second. At 20 radian per second, it is rotating in anti-clockwise direction. So under this situation, when the crank is making an angle of 60 degree with the horizontal, so under that situation, we have to find out that for the connecting rod, what are the velocities at the slider block end and at the crank end, and we have also find out that what is the velocity of the slider block. After that, you have to find out the angular velocity of that connecting rod. So already you have got all the necessary information and the data are provided. So now let us start solving the problem. So using our instrument, suitable instrument and suitable scaling factor, we have to draw this diagram first. Okay, so this length, this straight line which I have drawn, it is making an angle of 60 degree in the horizontal, that means this angle is 60 degree, and the length, how much I have to take? See, 480 millimeter of length, that you cannot draw in your copy. So what you can do, you can take the suitable scaling factor for this phase diagram, and what you can do, that you can use a scale of 1:20. Okay, 1:20 means, so whatever the distance of 480 millimeter you are having over here, it becomes 24, and over here 1600 millimeter, as you know. So if you divide it by 20, so it becomes 80 millimeter. Okay. So 24 millimeter will be your actual length in the drawing when you are drawing on your copy. So like that, you can draw that particular thing very easily. So scaling factor is a very important thing. And let me tell you one more thing, that there is no such hard and fast rule for selecting the scaling factor. Suitably and judiciously, we have to choose that what is the scaling factor I am going to take. So over here I have taken a scaling factor value of 1:20. scaling factor value of 1:20 for the space diagram. But if you want to take 1:10, 1:15, 1:25, that will also work. There is no problem. Okay, so now let us consider that this much amount of length is equal to 24 millimeter in your copy. Okay, I don't have that direct measurement option over here, so I am taking I'm using my common sense and geometrical sense. So this length I am considering as 24 millimeter, which is representing 480 millimeter over here. Again, this length, suppose so this length, that is over here, if you are considering AB, then this is BC and this is D and this is G. D is the slider block, the nomenclature is slider block, something like that, and C is the end C for the connecting rod over here. So everything is very simple, and from the diagram you already know that angle BAC or BAD, the angle ABC or angle ABD, angle ABC is greater than 90 degree. If you draw this picture or image properly, then you will find out it is greater than 90 degree. It has to happen. It will occur. So this angle is 90 degree over here. This angle is 60 degree over here, and it is rotating with omega dA, angular velocity, in anti-clockwise direction. So this is the crank, AB is the crank, which is rotating in anti-clockwise direction with angular velocity omega dA. What is the value of omega dA? That is 20 radian per second in anti-clockwise direction. Now BC, which is making an angle with AD and greater than 90 degree. So with respect to A, B is rotating in anti-clockwise direction. So with respect to B, C should rotate in clockwise direction. That is in the opposite direction. Clear? Now use your common sense that if crank is rotating in anti-clockwise direction, then in which direction this slider block will slide? By following the straight line path, it will slide in the left hand direction or right hand direction. You may pause the video over here and think for 10 seconds. Okay? Okay. If you are thinking that it is moving in the left hand direction, then you are right. It should move in the left hand direction because it is rotating in anti-clockwise direction. So everything connected to point B should move or should having a rotational or a translational or combination of both towards the left hand direction. So obviously it will drag the slider block in the left hand direction also. So definitely this particular slider block will also move towards the left hand direction. So now it's time to draw the velocity components. Okay, and then we are going to draw the velocity diagram. So for that purpose, what we are going to do? We are going to draw a line which is perpendicular, and this is the orientation of BBA. And with respect to B, because C is having a clockwise type of motion or rotational value, so definitely from point C over here, this angle is 90 degree and it is having a tendency of velocity component towards the left hand bottom direction, bottom and slightly left hand direction. And about the slider block, okay, which is having a connector at point C, it is having a tendency to move towards the okay. So now the picture looks somewhat like this. Velocity of C with reference to G. Okay, velocity of C with reference to G. Something like that. We got the entire orientation of the vector component of individual velocities which are acting at different parts of the different links. Okay, so now let us solve this problem, and we have to first draw the velocity diagram. Already over here we have shown the three velocity components, namely VBA, VCG and VCB. These three velocity components already we have shown over here. So properly, in correct method, using correct method, you have to first draw two mutually perpendicular axes using suitable instrument. You have to do not do it just by your common sense or just by your wish. Use suitably and properly this perpendicular component of vertical axis and horizontal axis. Then from this space diagram already you know which points are the static point or stable point or non-movable point. These non-movable points are point A and point G over here. So at the origin A and G we can write down. So this will be at point A and G are kept at the origin. Now VCG, which is acting in the left hand direction, so easily we can draw it like this. And this is the line of VCG. This is the line, because what is the length that I don't know. If it is a vector, then only I know the direction. I don't know the magnitude. Okay, so this is the line of VCG. But what about VBA? I know the direction, I know what is the magnitude. How I know the magnitude? Because what is the length AB? It is given. The length AB equal to 480 millimeter. So we know that VBA So you got the value of VBA, which is equal to 9600 milliliter per second, which is nothing but 9.6 meter per second also. Now what we can do, we can use a scaling factor again, and this time the scaling factor for the velocity diagram may consider as 1:100. That means you have to clearly mention that scaling factor 100 millimeter per second equal to 1 millimeter length. That means in reality, which is 100 millimeter per second, you are reproducing it as 1 millimeter of length. So 9600 millimeter per second, this particular amount of length is represented by only 96 millimeter of distance. So what we are going to do, we have to find out what is the angle which is creating over here, and then that particular angle we have to regenerate over here, and the length will be obviously 96 millimeter length. Okay, so it is very simple. So a local coordinate system we have drawn over here, and again so we got the point where they are intersected. They are intersected at this particular point. So rest of the part of the lines that we have traced, and we got the line of VBA. We got the line of VBA. Now comes the distance. We got the direction. Now got the distance. What should be the distance of VBA? That already I told you, that divided by 100 because we are using the scaling factor. So it will be 96 millimeter long. So from here to here we have to measure a distance or length of 96 millimeter. Suppose in your copy, up to this length equal to 96 millimeter. Suppose in your copy, up to this particular length is 96 millimeter. So you just keep it up to this length and erase or remove any extra other part. Okay? So up to this it is okay. So next is BCB. By the way, what is the name of this point? The name of this point is small b over here. This point is small b. So you got A, you got B, and you got G over here also. Now, small b, you have to, you got this point small b. Now you have to find out what is the BCB value. The process is same. We have to draw a vertical line, something like that. As I have shown over here, correctly you have to draw it, and then using a compass, you just take any arc length, and you have to take the same arc length again over here, same arc length. Now, on this vertical, you just put the compass, the needle over here, and cut the intersection point. And the same way, you have to cut the intersection point again over here. So this is the intersection point. So you erase or remove all other extra lines. So now you are going to join these two lines. From here to here, these 2 points you are connected. Now you see the horizontal line of BCG and this angular line of BCB, they are going to intersect in between. Okay, at this particular point. So erase or remove this part, erase or remove this part also. So from here to here, mention the direction. So this will be your VBA, this will be your VB, VCB, and this is VCG. Now the next method is simple. You measure this length and multiply with 100. You will get the actual value of velocity. Again you measure this length using your scale and multiply with 100. Because in this problem, in this particular problem, our scaling factor is 1:100. So that is why we are going to multiply it with 100. Okay? So the length in millimeter, multiply it in 100, you are going to get the actual velocity value in millimeter per second. Okay? So once you get the value in millimeter per second, then we know very well that omega CB, that should be equal to velocity CB divided by length CB. Velocity CB already you have found out. Length CB is already given in the problem, that is 1600. So you are going to get omega CB in radian per second. And in the same way, omega CG, that is equal to velocity CG divided by it is not required, I guess. Only this part is sufficient. So this is the only value which is required. Because otherwise, this velocity CG, there is no such omega value is created because it is not having any rotational component. It is reciprocating motion. This block is creating a reciprocating or linear motion. So there is no such thing which is rotating. So there is no question of angular velocity. So solve it by yourself and find out the answer. Okay, it's your task. Okay, so that's how we complete a particular numerical problem on a slider crank mechanism. Hope you enjoyed this video. Thank you very much.